Earth is the only known planet in the universe to harbor life, making it a remarkable and unique world. It's more than just a rocky sphere floating in space. It's a complex living system where physical, chemical, and biological processes intertwine to sustain an intricate biosphere. By studying Earth, we unlock the mysteries of life itself and gain insight into broader cosmic phenomena that shape planets across the universe. This exploration will delve deep into the structure, history, and systems of our home planet, illuminating how its unique characteristics fostered the development of life, the continual processes that shape its surface, and the ongoing challenges that humanity must navigate to ensure its survival. Earth formed about 4.54 billion years ago in the swirling accretion disk of gas and dust that surrounded the young sun. Over millions of years, particles in this disk collided and merged under the force of gravity, gradually forming larger bodies. One of these growing protoplanets became what we now know as Earth. Initially, our planet was a molten ball of magma hostile to any form of life. In these early stages, Earth's environment was far from hospitable. It was subjected to constant bombardment by meteors and asteroids, a process known as the late heavy bombardment, which played a significant role in shaping its surface and perhaps even delivering the water that would later become essential for life. Over time, Earth began to cool, allowing the formation of solid rock crust and, crucially, the emergence of liquid water, one of the most important ingredients for life. The formation of the Moon is a key event in Earth's early history. The prevailing theory, known as the giant impact hypothesis, suggests that a Mars-sized body named Theia collided with the early Earth. This cataclysmic event ejected vast amounts of material into space, which eventually coalesced to form our Moon. The Moon has had a profound influence on Earth ever since, stabilizing its axial tilt, which in turn stabilized the planet's climate and seasons, factors that were crucial in the development of life. In its infancy, Earth's atmosphere was vastly different from the one we breathe today. It was a thick, toxic mix of gases like methane, ammonia, and carbon dioxide. However, as the planet cooled, volcanic activity released massive amounts of water vapor, which eventually condensed to form Earth's oceans. These primordial oceans would later become the cradle of life. The presence of liquid water on Earth's surface is one of the most significant factors in its ability to support life. Water is not only essential for biological processes, but it also plays a critical role in regulating the planet's climate. The oceans act as vast reservoirs of heat, absorbing and redistributing energy from the sun, helping to maintain a relatively stable temperature range on Earth's surface. Earth is composed of several distinct layers, each contributing to its dynamic nature. At the surface lies the crust, a thin, solid shell of rocks and minerals upon which life exists. Beneath the crust is the mantle, a vast layer of semi-molten rock that slowly moves, driving the movement of tectonic plates. Deeper still lies the core, which is divided into a liquid outer core and a solid inner core, primarily composed of iron and nickel. The motion of molten iron within the outer core generates Earth's magnetic field, a vital shield that protects the planet from harmful solar radiation and cosmic particles. This magnetic field not only allows Earth to retain its atmosphere, but it also plays a crucial role in protecting life from radiation that would otherwise strip away our planet's protective ozone layer. One of Earth's most defining features is its tectonic activity. The surface of the Earth is divided into a mosaic of large and small plates that float atop the semi-fluid mantle. Over geological time, these plates drift, collide, and pull apart, giving rise to many of Earth's most dramatic features: mountain ranges, ocean basins, and earthquakes. This process, known as plate tectonics, is a fundamental driver of planetary change. Plate tectonics not only reshapes the planet's surface, but also plays a critical role in the carbon cycle, which regulates Earth's climate over millions of years. Through processes such as subduction, where one tectonic plate is forced beneath another, carbon trapped in rocks is recycled deep into the Earth's mantle, while volcanic activity releases carbon dioxide back into the atmosphere, balancing the greenhouse effect that keeps Earth warm. Earth's magnetic field extends from its core out into space, where it forms a protective barrier known as the magnetosphere. This field is generated by the movement of molten iron in the outer core, and it deflects charged particles from the sun, known as the solar wind. Without this magnetic shield, the solar wind would erode the atmosphere and expose Earth to dangerous levels of radiation, making life as we know it impossible. The study of Earth's magnetic field reveals much about the internal dynamics of our planet and its long-term evolution. It is also a reminder of how Earth's internal processes contribute to its habitability in ways that are often invisible but vital for life. Earth's atmosphere has undergone significant changes over its history. Initially composed of hydrogen and helium, these light gases were eventually lost to space due to the planet's weak gravity and solar winds. Volcanic outgassing replaced them with heavier gases, forming a thick atmosphere of water vapor, carbon dioxide, and nitrogen. This early atmosphere was inhospitable to life as we know it today. Around 2.4 billion years ago, a dramatic shift occurred with the Great Oxidation Event. Cyanobacteria, through the process of photosynthesis, began to produce oxygen as a byproduct, slowly transforming the atmosphere. This influx of oxygen enabled the development of more complex aerobic life forms and led to the creation of the ozone layer, which shields Earth from harmful ultraviolet radiation. Earth's atmosphere acts as a natural greenhouse, trapping heat and maintaining temperatures conducive to life. Without the greenhouse effect, Earth's surface would be too cold for liquid water, and life would not have emerged. Gases like carbon dioxide, methane, and water vapor allow sunlight to enter the atmosphere but prevent much of the heat from escaping back into space, thus warming the planet. While the greenhouse effect is crucial for maintaining a stable climate, human activities have altered this delicate balance. The burning of fossil fuels, deforestation, and industrial processes have significantly increased the concentration of greenhouse gases in the atmosphere, leading to global warming. The resulting climate changes, rising sea levels, more frequent extreme weather events, and shifting ecosystems pose serious challenges to life on Earth. Water is central to Earth's climate and its capacity to support life. The hydrological cycle describes the continuous movement of water on, above, and below the surface of the Earth. Driven by solar energy, water evaporates from oceans, lakes, and rivers, rises into the atmosphere, and returns to Earth as precipitation. This cycle not only distributes water across the globe, but also helps regulate temperature by transferring heat through evaporation and condensation. The interaction between the hydrological cycle and Earth's atmosphere influences weather patterns and climate. Water vapor, a potent greenhouse gas, plays a key role in the regulation of Earth's temperature. Understanding these processes is crucial for predicting how climate change will affect global water resources and ecosystems. Life on Earth likely began in the oceans about 3.8 billion years ago. The exact mechanisms by which life emerged remain one of the greatest scientific mysteries, but many scientists believe that life began in deep-sea hydrothermal vents, where mineral-rich water created the perfect conditions for the formation of complex organic molecules. From these humble beginnings, life evolved into the diverse biosphere we see today. The early biosphere consisted of simple, single-celled organisms that thrived in Earth's oceans. Over billions of years, these organisms evolved, eventually giving rise to the complex forms of life that now inhabit every corner of the planet. The diversity of life on Earth, from microscopic bacteria to towering redwood trees and massive whales, is a testament to the planet's ability to support an incredible range of biological systems. Earth's biosphere is a dynamic network of ecosystems, each filled with a myriad of species that interact in complex ways. Biodiversity, the variety of life on Earth, is essential for ecosystem health and resilience. Each species, no matter how small, plays a role in maintaining the balance of its ecosystem, whether through food webs, nutrient cycles, or pollination. Human activity, however, is threatening biodiversity on an unprecedented scale. Habitat destruction, pollution, overfishing, and climate change are driving many species to extinction. The loss of biodiversity not only diminishes the beauty and complexity of our natural world, but also undermines the very systems that sustain human life, from clean air and water to fertile soils and stable climates. Human activity has transformed Earth on a scale comparable to natural forces like tectonic activity or asteroid impacts. Some scientists have proposed that we are now living in a new geological epoch, the Anthropocene, characterized by humanity's profound influence on the planet's systems. We have altered landscapes, rerouted rivers, and changed the composition of the atmosphere and oceans. Our industrial activities have had particularly far-reaching effects. The burning of fossil fuels has released vast amounts of carbon dioxide into the atmosphere, leading to global warming and ocean acidification. Agricultural practices have reshaped ecosystems, while urbanization has led to habitat loss and fragmentation. Understanding these impacts is critical for developing sustainable solutions that will allow humanity to coexist with the natural world. Climate change represents one of the greatest challenges humanity has ever faced. The scientific consensus is clear. Human activities, particularly the burning of fossil fuels, are driving an unprecedented rate of warming. This warming is causing glaciers to melt, sea levels to rise, and weather patterns to become more extreme and unpredictable. The consequences of climate change will be felt across the globe, but the impacts will not be evenly distributed. Coastal cities face the threat of rising seas, while agricultural regions may experience more frequent droughts. Vulnerable populations in developing countries will be disproportionately affected, as they often lack the resources to adapt to these changes. Addressing climate change will require a coordinated global effort to reduce greenhouse gas emissions, protect ecosystems, and develop sustainable technologies. The future of Earth depends on the choices humanity makes today. We have the power to protect and restore the planet's ecosystems, reduce our carbon footprint, and transition to a sustainable economy that prioritizes environmental health alongside economic growth. However, this will require a fundamental shift in how we interact with the natural world. Sustainable development, conservation, and renewable energy are key pillars of a future where humans and nature can thrive together. Advances in technology, from carbon capture to renewable energy sources, offer hope that we can mitigate some of the damage we have done. But true change will require not only technological solutions, but also a cultural shift towards a more harmonious relationship with our planet. Earth's atmosphere is a thin layer of gases surrounding the planet, which not only makes life possible, but also plays a crucial role in climate and weather patterns. Composed primarily of nitrogen 78% and oxygen 21%, with trace amounts of carbon dioxide, water vapor, and other gases, the atmosphere shields the planet from the sun's harmful radiation while trapping enough heat to maintain a livable climate. Without the atmosphere, Earth would be an inhospitable, barren world. The balance of gases within the atmosphere is vital to maintaining the greenhouse effect, which ensures the planet remains warm enough for liquid water to exist. However, this balance is delicate, and human activities have caused significant disruptions. Earth's climate system is driven by the sun. Solar radiation heats the equator more intensely than the poles, creating differences in temperature and pressure that drive atmospheric circulation. This circulation redistributes heat around the planet, creating the diverse climate zones we experience, from tropical rainforests to arid deserts and icy polar regions. The circulation patterns of Earth's atmosphere, such as the Hadley, Ferrel, and polar cells, create predictable wind systems like the trade winds and westerlies. These winds, in turn, influence ocean currents, which transport heat and moisture across the globe. The interplay of atmospheric and oceanic circulation shapes weather patterns and helps regulate Earth's climate. The water cycle is a fundamental component of Earth's climate system. Solar energy causes water to evaporate from oceans, lakes, and rivers, rising into the atmosphere as water vapor. This vapor condenses into clouds, which release moisture as precipitation. The water returns to Earth's surface, replenishing rivers, lakes, and underground aquifers before eventually making its way back to the oceans. This cycle is crucial for distributing fresh water across the planet, supporting ecosystems and human civilizations alike. However, climate change is disrupting the water cycle, leading to more intense and unpredictable weather events such as floods, droughts, and hurricanes. The balance of the water cycle is increasingly under threat, impacting everything from agriculture to biodiversity. Oceans cover more than 70% of Earth's surface and play a key role in regulating the planet's climate. They act as giant heat sinks, absorbing solar energy and redistributing it through currents like the Gulf Stream, which carries warm water from the tropics to northern latitudes, moderating temperatures in regions like Western Europe. Oceans also absorb large amounts of carbon dioxide, helping to regulate the global carbon cycle. However, the oceans are not immune to human impact. Rising global temperatures are causing ocean waters to warm, which disrupts marine ecosystems and intensifies the frequency of extreme weather events. Furthermore, oceans are becoming more acidic due to the absorption of excess carbon dioxide from human activities, threatening coral reefs and other marine life. Life on Earth began in the oceans over 3.8 billion years ago, starting with simple single-celled organisms. Over billions of years, life evolved, becoming increasingly complex, eventually giving rise to the diverse biosphere that now covers every corner of the planet. The rise of multicellular organisms approximately 600 million years ago marked a pivotal point in this evolutionary journey, leading to the emergence of plants, animals, and, eventually, humans. The biosphere encompasses all living organisms on Earth, from microscopic bacteria to massive blue whales. It is an interconnected system where each species plays a role in maintaining the health of ecosystems. This diversity of life, or biodiversity, is essential for the resilience of ecosystems, allowing them to adapt to changes and disturbances. Ecosystems are the natural communities of organisms interacting with one another and their physical environment. From tropical rainforests and coral reefs to tundras and deserts, Earth's ecosystems are incredibly diverse. Each ecosystem is shaped by local climate, geography, and biological interactions. These systems provide essential services to humans, such as clean air, water, and food, as well as cultural and recreational value. Biodiversity, the variety of species within an ecosystem, is a critical measure of its health. The more diverse an ecosystem, the more resilient it is to disturbances such as disease or climate change. However, human activity is rapidly eroding biodiversity. Habitat destruction, pollution, overfishing, and climate change are driving an unprecedented wave of extinctions, threatening the stability of ecosystems worldwide. The carbon and nitrogen cycles are fundamental to life on Earth, regulating the availability of essential elements that organisms need to survive. The carbon cycle involves the movement of carbon between the atmosphere, oceans, soil, and living organisms. Plants absorb carbon dioxide from the atmosphere during photosynthesis, storing it in their tissues. When plants die or are consumed, the carbon is released back into the atmosphere, completing the cycle. The nitrogen cycle, meanwhile, is essential for producing proteins and DNA, the building blocks of life. Nitrogen makes up about 78% of the atmosphere, but most organisms cannot use nitrogen in its gaseous form. Certain bacteria in the soil convert nitrogen into compounds that plants can absorb, which then make their way up the food chain. Human activities, such as burning fossil fuels and industrial agriculture, have disrupted both the carbon and nitrogen cycles, contributing to climate change and environmental degradation. The overuse of fertilizers, for instance, has led to nitrogen runoff into rivers and oceans, causing dead zones where oxygen levels are too low to support life. Human beings have become the dominant force shaping the planet's environment, to the extent that many scientists believe we have entered a new geological epoch, the Anthropocene. This era is characterized by the profound and often irreversible impact of human activity on Earth systems, whether it be through deforestation, pollution, climate change, or the extinction of species. Since the Industrial Revolution, humanity's footprint has grown exponentially. We have transformed landscapes on a massive scale, altered the chemistry of the atmosphere and oceans, and driven thousands of species to extinction. The Anthropocene is a sobering reminder of both the power and the responsibility humanity holds as stewards of the planet. The most pressing consequence of human activity is climate change. The burning of fossil fuels, deforestation, and industrial agriculture have dramatically increased the concentration of greenhouse gases in the atmosphere, trapping more heat and causing global temperatures to rise. This has led to a cascade of effects, including melting polar ice caps, rising sea levels, more intense storms, and shifting weather patterns. Climate change threatens not only natural ecosystems, but also human societies. Rising sea levels are putting coastal cities at risk, while droughts and heat waves are impacting agriculture and food security. The Arctic is warming at twice the rate of the rest of the planet, with profound implications for global weather patterns. If left unchecked, climate change could disrupt the delicate balance of Earth's systems in ways that are difficult to predict. Human expansion and development have led to widespread habitat destruction, from the deforestation of the Amazon rainforest to the conversion of wetlands into agricultural land. As habitats are destroyed or fragmented, the species that depend on them face increasing pressure, often leading to extinction. Scientists estimate that we are currently in the midst of the sixth mass extinction, with species disappearing at a rate 100 to 1. 1,000 times faster than the natural background rate. The loss of biodiversity has far-reaching consequences. Ecosystems are interconnected, and the extinction of one species can lead to the collapse of others. For example, the decline of pollinators such as bees threatens global food production, while the loss of predators can lead to overpopulation of prey species, disrupting entire ecosystems. Pollution in its many forms is another significant human impact on Earth. Air pollution from industrial emissions and vehicle exhaust contributes to respiratory diseases and premature deaths. In developing countries, indoor air pollution from cooking fires is a major public health issue. Meanwhile, plastic pollution has become a global crisis, with millions of tons of plastic waste ending up in the oceans each year, harming marine life and entering the food chain. Chemical pollutants, such as pesticides and heavy metals, have also had devastating effects on ecosystems. In the oceans, chemical runoff from agriculture has created dead zones, areas where oxygen levels are too low to support most marine life. The cumulative effects of pollution are altering the chemistry of Earth's air, water, and soil, threatening both human health and the environment. One of the most promising solutions to mitigate climate change is the transition to renewable energy sources. Solar, wind, hydroelectric, and geothermal power offer cleaner alternatives to fossil fuels, reducing greenhouse gas emissions and decreasing our dependence on finite resources. Advances in technology have made renewable energy more affordable and efficient, paving the way for a sustainable energy future. The shift to renewable energy is not without challenges, particularly in terms of infrastructure and storage. Solar and wind power, for example, are intermittent sources of energy, meaning they are not always available when demand is high. However, innovations in battery storage and smart grid technology are helping to overcome these obstacles, bringing us closer to a world powered by renewable energy. Protected areas, such as national parks and marine reserves, provide sanctuaries where ecosystems can thrive without the pressures of human encroachment. These areas serve as reservoirs of biodiversity, safeguarding species that are otherwise threatened by habitat destruction. However, conservation must extend beyond these designated spaces. To be effective, efforts must include restoring degraded lands and protecting critical habitats that lie outside the boundaries of protected areas. Reforestation, the process of planting trees in deforested or degraded landscapes, is one of the most effective strategies for combating climate change and biodiversity loss. Forests act as carbon sinks, absorbing significant amounts of carbon dioxide from the atmosphere and helping to mitigate global warming. Moreover, forests are home to over 80% of terrestrial species, making them essential for preserving biodiversity. Initiatives like the Bond Challenge and the Trillion Trees campaign aim to restore millions of hectares of forest globally, not only to sequester carbon but to revitalize ecosystems and provide livelihoods for local communities. Agroforestry, a sustainable farming practice that integrates trees into agricultural systems, also offers a promising solution. By planting trees alongside crops, farmers can enhance soil fertility, reduce erosion, and improve water retention, all while sequestering carbon and increasing biodiversity on agricultural lands. These practices demonstrate that conservation and human development can go hand in hand, creating a sustainable future for both people and the planet. A shift toward a circular economy is essential to reduce humanity's ecological footprint. In the current linear model of consumption, resources are extracted, used, and then discarded, often ending up in landfills or oceans. This unsustainable system depletes natural resources and generates vast amounts of waste. The circular economy, by contrast, focuses on designing products that can be reused, repaired, and recycled, keeping materials in circulation for as long as possible. In the circular economy, waste is seen not as an inevitable byproduct, but as a resource. For example, organic waste can be composted to enrich soils, while plastic can be recycled into new products, reducing the need for virgin materials. Companies are increasingly adopting sustainable design principles, using renewable materials, and creating products that are easier to repair and recycle. Consumers, too, play a role in this transition by choosing sustainable products, reducing waste, and embracing a mindset of conservation and reuse. Technological innovations, such as advanced recycling methods and biodegradable materials, are helping to make the circular economy a reality. However, systemic changes are needed at all levels, from government policies that incentivize sustainable practices to corporate responsibility for reducing environmental impact. Ultimately, the transition to a circular economy offers a path to a more sustainable future, where economic growth is decoupled from resource depletion. As the global population continues to grow, ensuring food security without further degrading Earth's ecosystems is a significant challenge. Agriculture is a major driver of deforestation, biodiversity loss, and greenhouse gas emissions, yet it is essential for feeding the planet. Sustainable agriculture seeks to balance the need for food production with environmental stewardship, using practices that protect soil health, conserve water, and minimize the use of harmful chemicals. One approach is regenerative agriculture, which focuses on restoring soil health through techniques such as crop rotation, cover cropping, and reduced tillage. Healthy soils sequester more carbon, retain water more effectively, and support higher levels of biodiversity. Organic farming, which avoids synthetic pesticides and fertilizers, also contributes to healthier ecosystems and reduces pollution. Additionally, precision agriculture, which uses technology to monitor crop health and optimize resource use, can increase efficiency and reduce environmental impact. Aquaculture, or the farming of fish and other aquatic species, offers another avenue for sustainable food production. When managed responsibly, aquaculture can provide a reliable source of protein with a lower environmental footprint than traditional livestock farming. However, unsustainable practices in aquaculture, such as overuse of antibiotics and destruction of coastal ecosystems, must be addressed to ensure that it remains a viable and sustainable option. The challenge of feeding a growing population will also require reducing food waste, which accounts for roughly 1/3 of all food produced globally. Innovations in food storage, transportation, and distribution, along with changes in consumer behavior, are critical to reducing waste and ensuring that food reaches those who need it most. While efforts to mitigate climate change are critical, the reality is that some level of warming is already inevitable. This makes adaptation, preparing for and responding to the impacts of climate change, an essential component of global climate strategy. Climate resilience involves strengthening the ability of ecosystems, communities, and infrastructure to withstand and recover from climate-related shocks. Coastal regions, for example, are particularly vulnerable to rising sea levels and more frequent storms. Building resilient infrastructure such as seawalls and storm-resistant buildings can help protect these areas. At the same time, restoring natural barriers such as mangroves and wetlands can provide additional protection by absorbing storm surges and reducing erosion. In agriculture, developing drought-resistant crops and improving water management systems will be essential for maintaining food production in a changing climate. Urban areas too must adapt by implementing green infrastructure such as parks and green roofs, which can reduce heat and improve air quality. Climate resilience requires proactive planning, investment in sustainable infrastructure, and a commitment to protecting the most vulnerable populations. Technology will play a critical role in addressing the environmental challenges of the 21st century. From renewable energy to artificial intelligence, technological innovations offer new tools for reducing environmental impact and improving sustainability. Advances in clean energy technologies, such as solar panels, wind turbines, and battery storage, are making it easier and more cost-effective to transition away from fossil fuels. In addition to energy, technology is transforming how we manage natural resources. Satellite imagery and remote sensing technologies allow scientists to monitor deforestation, track wildlife populations, and assess the health of ecosystems in real time. This data can inform conservation efforts, enabling more targeted and effective interventions. Artificial intelligence and machine learning are also being used to optimize resource use in industries like agriculture and manufacturing. For example, AI can help farmers determine the optimal amount of water and fertilizer for crops, reducing waste and improving yields. In cities, smart grid technology can improve energy efficiency by dynamically adjusting power distribution based on real-time demand. However, technology alone will not solve the planet's environmental problems. It must be paired with thoughtful policies, ethical considerations, and global cooperation to ensure that technological advancements benefit both people and the planet. Ensuring equitable access to these technologies, especially in developing countries, will be crucial for creating a sustainable and just future. The environmental challenges we face are global in nature, and addressing them requires international cooperation. Climate change, biodiversity loss, and pollution do not respect national borders, and no single country can solve these problems alone. Global agreements, such as the Paris Climate Agreement, represent important steps towards collective action, but much more is needed to meet the scale of the challenge. International cooperation must extend beyond governments to include businesses, non-governmental organizations, and civil society. Corporations, in particular, have a significant role to play in reducing environmental impact. Many companies are now adopting sustainability goals, reducing emissions and transitioning to renewable energy. However, voluntary actions by a few companies will not be enough. Governments must implement regulations and incentives to ensure that all industries contribute to environmental sustainability. Public engagement and education are also key to driving global action. A well-informed public is more likely to support policies and practices that protect the environment. Educational initiatives, from schools to community programs, can help people understand the importance of sustainability and how they can make a difference in their own lives. At the heart of all these efforts lies a shift in our relationship with the planet, a move from exploitation to stewardship. The future of Earth depends on our ability to recognize that we are not separate from the natural world, but part of it. Our well-being is inextricably linked to the health of the planet, and we have a moral responsibility to care for the Earth not only for our own benefit but for future generations and the countless species with whom we share this world. Stewardship is not just about reducing harm. It is about actively restoring and protecting the systems that sustain life. It requires rethinking how we live, from the energy we use to the food we eat, and recognizing that sustainability is not a choice but a necessity. By embracing a new ethic of stewardship, we can create a future where both people and the planet thrive. Earth orbits the Sun as the third planet in a system of 8 planets, countless smaller bodies, and the vast expanse of the Kuiper Belt. It occupies a special position in what is known as the habitable zone, or the Goldilocks zone, where conditions are neither too hot nor too cold for liquid water to exist. This fortuitous position is one of the key reasons why life flourished on Earth and not on neighboring planets like Venus or Mars. Unlike its planetary neighbors, Earth has the right combination of atmosphere, temperature, and liquid water to support life. Venus, with its thick atmosphere and runaway greenhouse effect, is a scorching inferno, while Mars, though once more Earth-like, is now a cold, dry desert world. Earth's unique conditions arose from a delicate interplay of factors, including its distance from the Sun, its geological activity, and the presence of water. The Sun itself is a relatively stable star, providing Earth with consistent energy over billions of years. While solar flares and occasional changes in solar output can affect Earth's climate and technology, the long-term stability of our star has been critical for the development of life. This cosmic harmony, however, is not guaranteed forever. Earth's relationship with its moon is another factor that has played a vital role in the stability of life on our planet. The Moon, believed to have formed from debris after a massive collision between Earth and a Mars-sized body, has helped stabilize Earth's axial tilt over long timescales. This tilt is responsible for the changing seasons, which, in turn, have influenced biological cycles and evolution. Without the Moon, Earth's axis could wobble chaotically, leading to extreme climate swings that might have made the development of complex life far more difficult, if not impossible. The Moon's gravitational pull also drives the ocean tides, which have shaped coastal ecosystems and influenced the behavior of marine life for billions of years. The ebb and flow of the tides may have even played a role in the transition of life from sea to land. However, the Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. While this will have little immediate impact, over millions of years, it will continue to alter the length of Earth's days and the intensity of tidal forces. This relationship, like many on Earth, is dynamic and evolving, reminding us that our planet is part of a larger, interconnected system that is constantly in flux. Earth's magnetic field, generated by the movement of molten iron in its outer core, extends far into space and acts as a protective shield against harmful solar and cosmic radiation. Known as the magnetosphere, this invisible barrier deflects charged particles from the Sun, preventing them from stripping away the atmosphere and bombarding the surface with deadly radiation. Without this magnetic shield, Earth would likely resemble Mars, which lost much of its atmosphere to solar winds long ago. The magnetic field also creates spectacular phenomena known as auroras, as solar particles interact with Earth's atmosphere near the poles, producing stunning displays of light in the night sky. Yet, Earth's magnetic field is not static. Over geological timescales, it has reversed many times, with the magnetic north and south poles swapping places. These geomagnetic reversals are recorded in the magnetic patterns of ancient rocks and provide scientists with important clues about the planet's interior. Though these reversals are irregular and can take thousands of years to complete, they serve as a reminder that Earth's systems are dynamic and ever-changing. Earth's current stability is a fleeting moment in its long, cosmic journey. Over the next few billion years, the Sun will continue to grow brighter as it ages, gradually increasing the temperature on Earth. In about 1 billion years, the Sun's luminosity will likely increase to the point where the Earth's oceans will begin to evaporate, leading to a runaway greenhouse effect similar to Venus. Eventually, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets, including Earth. While this transformation is billions of years away, it underscores the temporary nature of Earth's habitability. Long before this point, human civilization, if it still exists, will have to confront the need to move beyond Earth if we wish to survive. This distant future highlights the importance of space exploration and the search for habitable planets beyond our solar system. While Earth is currently our only home, the cosmos is vast, and other worlds may offer a refuge for humanity if we learn how to navigate the challenges of space travel and planetary colonization. One of the most profound questions that humanity has ever asked is, are we alone in the universe? The discovery of thousands of exoplanets, planets orbiting other stars, has revolutionized our understanding of the cosmos and opened up new possibilities for finding life beyond Earth. With missions like NASA's Kepler and TESS transiting exoplanet survey satellite, astronomers have identified planets in the habitable zones of their stars, where conditions might be right for liquid water and potentially life. These discoveries suggest that Earth is not unique in the universe. There may be billions of Earth-like planets in our galaxy alone, each with the potential to host life. However, detecting life on these distant worlds remains a challenge. Scientists are developing new techniques to analyze the atmospheres of exoplanets, looking for biosignatures, chemical signs of life, such as oxygen, methane, or other gases that could indicate biological processes. The James Webb Space Telescope, launched to explore the universe in unprecedented detail, is expected to play a key role in this quest. It will allow scientists to probe the atmospheres of distant exoplanets and search for signs of habitability. If life is discovered on another world, it would fundamentally change our understanding of our place in the universe and our relationship with Earth. While the discovery of exoplanets suggests that potentially habitable worlds are common, the conditions that made life possible on Earth are extremely delicate. From the stability of our star to the presence of a large moon and a protective magnetic field, Earth benefits from a rare combination of factors that have allowed life to flourish. Even minor changes in these conditions could have rendered our planet barren. This fragility underscores the need to protect Earth's biosphere. While we may eventually find life elsewhere in the universe, Earth is currently the only planet we know that can support human life. The search for extraterrestrial life is a reminder of how precious our world is and how much we have to lose if we fail to protect it. The sheer number of potentially habitable planets raises another intriguing question. If life is common in the universe, why haven't we found any evidence of extraterrestrial civilizations? This question, known as the Fermi paradox, has puzzled scientists and philosophers for decades. There are many possible explanations for the Fermi paradox. Perhaps intelligent civilizations are rare, or maybe they destroy themselves before they can explore the cosmos. It's also possible that advanced civilizations are avoiding us, or that we are simply not looking in the right way. The answers to these questions could reshape our understanding of life in the universe, and of our own future on Earth. In the meantime, Earth remains a solitary beacon of life in the vastness of space. Its blue oceans and green forests a stark contrast to the lifeless worlds around us. As the dominant species on Earth, humanity now holds unprecedented power over the future of the planet. The Anthropocene, the current geological epoch in which human activity is the primary driver of environmental change, places a heavy responsibility on our shoulders. Our actions, whether it's burning fossil fuels, clearing forests, or polluting the oceans, are reshaping the planet in ways that will affect not only us, but all life on Earth for generations to come. This age of responsibility requires a shift in mindset. We must recognize that we are not separate from the natural world, but a part of it. The health of the planet is inextricably linked to our own well-being. Protecting Earth's ecosystems, combating climate change, and ensuring the sustainable use of resources are not just environmental issues, they are existential issues for humanity. Achieving a sustainable future for Earth requires both education and action. Understanding the science of climate change, biodiversity, and resource management is critical to making informed decisions, but knowledge alone is not enough. It must be paired with action at all levels of society, from individual choices to global policies. In education, a new generation of leaders and thinkers must be equipped with the skills and knowledge to navigate the environmental challenges of the 21st century. This includes fostering a sense of global citizenship, where people recognize their role in the broader Earth system and feel empowered to make a difference. The path to sustainability is complex, but with collective action it is within our reach. While the environmental challenges facing Earth are daunting, there is also reason for hope. Across the globe, communities, businesses, and governments are taking bold steps to reduce emissions, protect biodiversity, and transition to sustainable practices. Advances in renewable energy, conservation efforts, and international agreements, such as the Paris Climate Agreement, show that positive change is possible. Perhaps the greatest source of hope lies in our ability to learn from the past and adapt to new challenges. Humanity has shown remarkable resilience and ingenuity throughout history, and we have the capacity to rise to the challenge of protecting our planet. A planetary awakening is taking place, as more people recognize the urgent need to act and the profound connection between the health of the Earth and the future of humanity. Earth's history is a testament to its capacity for change. Over billions of years, the planet has experienced dramatic shifts in climate, from the frozen expanse of snowball Earth to the warm, humid world of the Cretaceous period. These transformations are driven by natural processes such as volcanic activity, variations in Earth's orbit, and shifts in atmospheric composition. While these changes often unfold over millions of years, they remind us that Earth's environment is not static. One of the most important drivers of Earth's long-term climate cycles is the Milankovitch cycles, periodic changes in Earth's orbit and axial tilt that influence the amount of solar energy reaching the planet. These cycles have played a key role in the timing of ice ages and interglacial periods over the past few million years, contributing to the planet's natural rhythm of warming and cooling. However, the rapid pace of modern climate change is unprecedented in Earth's recent history. While past climate shifts occurred over millennia, human activities are driving changes within just a few centuries. This accelerated warming is outpacing the ability of many species and ecosystems to adapt, raising mistakes for future generations. Earth has experienced 5 mass extinction events, each of which wiped out a significant portion of life on the planet. These events, caused by factors such as asteroid impacts, volcanic activity, and climate shifts, radically altered the course of evolution, creating opportunities for new species to emerge while others perished. The most well-known of these events is the Cretaceous-Paleogenic KPG extinction, which occurred around 66 million years ago and led to the demise of the dinosaurs. This event was triggered by a massive asteroid impact, which caused a global climate catastrophe. Dust and aerosols thrown into the atmosphere blocked sunlight, cooled the planet, and disrupting ecosystems. Today, scientists warn that we may be entering a 6th mass extinction, this time driven by human activity. Habitat destruction, climate change, pollution, and overexploitation of natural resources are pushing species to the brink. The loss of biodiversity is not just a tragedy for nature, it also threatens the stability of ecosystems that provide essential services for humanity, from pollination to clean water. Learning from the past, we can see that Earth has always rebounded from extinction events, but it has taken millions of years to do so. The current trajectory of biodiversity loss, if unchecked, could set back ecosystems for millennia, with profound consequences for human survival. Over the past 2.6 million years, Earth has been in an ice age known as the Quaternary period, characterized by cycles of glacial and interglacial periods. During glacial periods, large portions of the planet were covered in ice sheets, while interglacial periods, such as the one we are currently in, have seen warmer temperatures and the retreat of glaciers. These natural cycles are driven by variations in Earth's orbit, as well as feedback mechanisms involving ice cover, ocean currents, and atmospheric carbon dioxide levels. The transition from the last glacial period, which ended around 12,000 years ago, to the current interglacial period allowed human civilizations to flourish. Stable climates, fertile land, and rising sea levels created the conditions for agriculture and the growth of cities. However, human-induced climate change is now disrupting these natural cycles. As global temperatures rise, ice sheets in Greenland and Antarctica are melting at alarming rates, contributing to rising sea levels. The melting of these ice sheets not only threatens coastal cities but also has the potential to disrupt ocean currents that regulate global climate. The consequences of these disruptions could be far-reaching, affecting weather patterns, agricultural productivity, and the distribution of species. Earth's resources, from fresh water and fertile soil to minerals and fossil fuels, are the foundation of human civilization. For thousands of years, humans have extracted these resources to build societies, fuel economies, and support growing populations. However, many of these resources are finite, and the unsustainable rate at which we are consuming them is leading to resource depletion and environmental degradation. Fossil fuels such as coal, oil, and natural gas have powered the Industrial Revolution in the modern world, but their extraction and use come at a steep environmental cost. Burning fossil fuels releases greenhouse gases into the atmosphere, driving climate change, while mining and drilling degrade landscapes and pollute water supplies. Moreover, fossil fuel reserves are limited, and as they become scarcer, the world will need to transition to renewable energy sources. Water, too, is a critical but limited resource. While Earth is often called the blue planet because of its abundant oceans, only a small fraction of the planet's water is fresh and accessible for human use. Agriculture, industry, and growing populations are placing increasing pressure on freshwater supplies, leading to water scarcity in many regions. In the coming decades, water management will become one of the most pressing challenges for humanity, as climate change exacerbates droughts and shifts rainfall patterns. Sustainable resource management is essential for preserving Earth's natural wealth for future generations. This approach involves balancing the needs of human societies with the health of ecosystems, ensuring that resources are used efficiently and responsibly. It also requires recognizing the limits of what Earth can provide and finding ways to reduce consumption, recycle materials, and minimize waste. In energy, the transition to renewable sources such as solar, wind, and geothermal power offers a pathway to reducing reliance on fossil fuels. Renewable energy is abundant and, unlike fossil fuels, does not produce harmful emissions or deplete finite resources. Advances in energy storage and grid technology are making it easier to integrate renewable energy into the global power supply, offering hope for a future where energy needs are met sustainably. In agriculture, sustainable practices such as crop rotation, organic farming, and permaculture can help protect soil health, conserve water, and reduce the environmental impact of food production. Innovations in precision agriculture, which uses technology to monitor and manage crops more efficiently, can also play a role in reducing waste and increasing yields while minimizing the use of fertilizers and pesticides. Forests, oceans, and other ecosystems provide invaluable services, from sequestering carbon to supporting biodiversity. Protecting these natural resources through conservation efforts, reforestation, and sustainable fishing practices is critical for maintaining the balance of Earth's systems and ensuring that future generations can enjoy the same benefits. The concept of a circular economy offers a transformative vision for how we use Earth's resources. In a traditional linear economy, materials are extracted, used, and then discarded as waste. This model is unsustainable as it depletes resources and generates pollution. In contrast, a circular economy seeks to keep materials in use for as long as possible, minimizing waste and reducing the need for new resource extraction. In a circular economy, products are designed to be durable, repairable, and recyclable. Materials are recovered and reused, creating a closed-loop system that mimics the cycles of nature. This approach not only conserves resources, but also reduces the environmental impact of manufacturing and waste disposal. For example, recycling metals from electronic devices can reduce the need for mining, while composting organic waste returns valuable nutrients to the soil. Governments, businesses, and consumers all play a role in building a circular economy. Policies that promote recycling, ban single-use plastics, and incentivize sustainable product design can drive the transition. Companies can innovate by developing products that are easier to recycle and by adopting business models that prioritize repair and reuse over disposal. Consumers, too, can contribute by making mindful choices about the products they buy and how they dispose of them. The future of Earth depends on the actions we take today. While the challenges we face are significant, they are not insurmountable. Sustainability offers a guiding principle for how humanity can live in harmony with the planet, ensuring that the resources and ecosystems that support life are preserved for future generations. Achieving sustainability will require systemic changes across all sectors of society, from energy and agriculture to transportation and waste management. It will also require a shift in values where the health of the planet is prioritized alongside economic growth. This transformation will not be easy, but it is necessary if we are to create a future where both people and the planet can thrive. Innovation and technology will play a critical role in this transition. Advances in renewable energy, carbon capture, sustainable agriculture, and resource management offer new tools for reducing our environmental footprint. However, technology alone is not enough. Political will, international cooperation, and public engagement are essential to driving the changes needed to build a sustainable future. Education is one of the most powerful tools we have for shaping the future. By teaching the next generation about the importance of sustainability, climate science, and environmental stewardship, we can empower young people to become the leaders of tomorrow. Environmental education should be a core part of curricula around the world, fostering a deep connection with nature and a sense of responsibility for protecting the planet. Global cooperation is also essential for addressing environmental challenges that transcend national borders. Climate change, biodiversity loss, and pollution are global problems that require coordinated international action. Agreements such as the Paris Climate Agreement and initiatives like the United Nations Sustainable Development Goals provide frameworks for collaboration, but achieving these goals will require sustained commitment from all nations. At the same time, solutions must be tailored to the needs and circumstances of individual countries and communities. What works in one region may not be applicable in another, and equity must be at the heart of any global environmental strategy. Developing nations, in particular, will need support to transition to sustainable practices without sacrificing economic growth and development. As we look to the future, we must imagine a world where humanity lives in harmony with the natural world. This vision includes cities powered by renewable energy, where green spaces, efficient public transportation, and sustainable architecture are the norm. It includes agricultural systems that regenerate the land rather than deplete it, and oceans teeming with life rather than choked by plastic. In this future, we have not only slowed the pace of climate change, but have begun to reverse its effects, restoring ecosystems and rewilding landscapes. Biodiversity thrives, and species that were once on the brink of extinction have rebounded. Clean air and water are available to all, and the circular economy ensures that resources are used wisely and waste is minimized. This vision is not utopian, it is achievable. The tools and knowledge we need to create a sustainable future already exist. What is required is the collective will to act, to prioritize the long-term health of the planet over short-term gains, and to recognize that the fate of humanity is inextricably linked to the fate of Earth. One of the most fascinating ideas about Earth is the Gaia hypothesis, proposed by scientist James Lovelock in the 1970s. This hypothesis suggests that Earth behaves like a living organism, with its biological and physical components interacting to regulate the conditions necessary for life. The atmosphere, oceans, land, and living organisms work together to maintain a balance that supports life, a dynamic equilibrium that has persisted for billions of years. The Gaia hypothesis emphasizes that Earth's systems are interconnected. For example, plants absorb carbon dioxide and release oxygen, which animals need to survive, while animals exhale carbon dioxide that plants use for photosynthesis. This reciprocal relationship between organisms and their environment is a central feature of life on Earth. Critically, the Gaia hypothesis also underscores the fragility of these self-regulating systems. Human activities, deforestation, industrialization, pollution, are altering the delicate balance that has made Earth so hospitable. Climate change, in particular, is disrupting the finely tuned processes that have maintained Earth's temperature and atmospheric composition. If these systems are pushed too far, the planet's ability to support life as we know it could be compromised. At the heart of Earth's self-regulating nature are feedback loops, processes that either amplify or dampen changes within the planet's systems. Positive feedback loops, such as the melting of polar ice, can accelerate changes. As ice melts, it reduces the planet's albedo reflectivity, meaning less sunlight is reflected back into space, which leads to further warming and more ice melt. This creates a vicious cycle that accelerates climate change. On the other hand, negative feedback loops help stabilize Earth's climate and ecosystems. For example, increased levels of carbon dioxide can stimulate plant growth, as plants absorb CO2 for photosynthesis. This in turn can reduce the amount of carbon dioxide in the atmosphere, helping to mitigate global warming. These feedback mechanisms illustrate the complexity of Earth's systems and the challenges of predicting how they will respond to human-induced changes. Small disruptions in one part of the system can have far-reaching consequences, setting off a chain reaction that affects the entire planet. Understanding these feedback loops is critical for managing Earth's future and mitigating the effects of climate change. The biosphere is the thin layer of Earth where life exists, extending from the deepest ocean trenches to the upper atmosphere. It is a complex and dynamic system in which organisms interact with each other and their physical environment. The biosphere is powered by the sun, with plants and other photosynthetic organisms converting solar energy into the chemical energy that fuels life on Earth. Earth's biosphere is unique in the known universe. While scientists have found potential biosignatures on distant exoplanets, no other planet we know of has the same combination of liquid water, stable climate, and complex ecosystems that support life. The diversity of life on Earth, from the smallest microbes to the largest mammals, is a testament to the planet's ability to foster and sustain life in a wide range of environments. The health of the biosphere is directly linked to The Anthropocene is a term used to describe the current geological epoch, in which human activity has become the dominant influence on Earth's climate and ecosystems. Although it is still debated whether the Anthropocene should be officially recognized as a new epoch, there is no denying a profound impact that humans have had on the planet. From the Industrial Revolution to the digital age, humanity's footprint on Earth has grown exponentially. Deforestation, urbanization, the spread of agriculture, and the extraction of natural resources have transformed vast landscapes. The atmosphere and oceans bear the chemical signatures of human activity with elevated levels of carbon dioxide, nitrogen, and pollutants. Even the geological record is now marked by human artifacts, such as plastic waste, concrete, and radioactive isotopes from nuclear tests. The Anthropocene raises important ethical and philosophical questions about humanity's role on Earth. As the dominant species, we have the power to shape the future of the planet, but with that power comes responsibility. How do we balance the needs of human civilization with the need to protect Earth's ecosystems? And how can we ensure that future generations inherit a planet that is capable of sustaining life? The period since the mid-20th century has been described as the Great Acceleration, a time of rapid economic growth, technological advancement, and population increase. During this time, humanity's impact on Earth's systems has intensified, driven by industrialization, globalization, and the rise of consumer culture. The Great Acceleration has brought tremendous benefits in terms of improved living standards, medical advancements, and technological innovation. However, it has also come at a great cost to the environment. Greenhouse gas emissions have soared, leading to unprecedented levels of atmospheric carbon dioxide and global warming. Land use changes such as deforestation and urban sprawl have driven species extinction rates to levels not seen since the last mass extinction. The Great Acceleration highlights the urgent need for a new approach to development, one that is sustainable and equitable. It challenges us to rethink our relationship with the planet and to find ways to decouple economic growth from environmental degradation. The future of the Anthropocene will depend on our ability to transition to sustainable practices that respect Earth's limits. The concept of planetary boundaries, introduced by a group of Earth system scientists, provides a framework for understanding the limits of human activity on Earth. These boundaries define the safe operating space for humanity, within which the planet's systems can continue to function in a stable and resilient manner. 9 planetary boundaries have been identified, including climate change, biodiversity loss, land system change, freshwater use, and chemical pollution. Crossing these boundaries increases the risk of destabilizing Earth's systems, leading to potentially catastrophic consequences for human society and the natural world. Currently, humanity has already crossed several of these boundaries, most notably in the areas of climate change and biodiversity loss. The challenge for the future is to bring human activities back within safe limits, while still meeting the needs of a growing global population. This will require transformative changes in how we produce energy, grow food, manage resources, and govern societies. The concept of the global commons refers to the shared resources that are available to all of humanity, such as the atmosphere, oceans, and polar regions. These commons are essential for the survival of life on Earth, but they are also vulnerable to overuse and degradation. Protecting the global commons is one of the most pressing challenges of the Anthropocene. The tragedy of the commons, a situation in which individuals exploit a shared resource for their own benefit, leading to its depletion, can be seen in the overfishing of oceans, the deforestation of tropical rainforests, and the accumulation of greenhouse gases in the atmosphere. To prevent the collapse of the global commons, international cooperation and collective action are essential. Efforts to manage the global commons, such as the United Nations Framework Convention on Climate Change and the Convention on Biological Diversity, have made progress in setting international goals for protecting the environment. However, much more needs to be done to ensure that these agreements are implemented effectively, and that the global commons are managed in a way that benefits all of humanity, especially future generations. The future of Earth and the Anthropocene will be shaped by the choices humanity makes in the coming decades. To ensure a livable planet, we must reimagine what progress means, moving away from a model of endless economic growth and resource extraction toward one that prioritizes sustainability, equity, and well-being. Sustainable development aims to meet the needs of the present without compromising the ability of future generations to meet their own needs. This requires a fundamental shift in how we produce and consume, placing greater value on renewable resources, circular economies, and the health of ecosystems. It also means addressing social inequalities. as the impacts of environmental degradation disproportionately affect the world's most vulnerable populations. Technological innovation, while crucial, must be guided by ethical considerations and a long-term vision for planetary health. Advances in fields such as renewable energy, sustainable agriculture, and green infrastructure offer hope for a future where human development and environmental protection go hand in hand. But technology alone cannot solve the challenges of the Anthropocene. Cultural, political, and economic changes are equally important. In the Anthropocene, the fate of nations is increasingly intertwined. Global problems like climate change, biodiversity loss, and ocean acidification require global solutions. The concept of planetary governance is gaining traction as a way to manage the global commons and address environmental challenges on a planetary scale. Effective planetary governance will require international cooperation, shared accountability, and the recognition that environmental issues are deeply connected to social and economic issues. Multilateral agreements, such as the Paris Climate Accord, represent important steps in the right direction, but stronger enforcement mechanisms and broader participation are needed. At the same time, planetary governance must be inclusive and just. Developing nations, which have contributed the least to environmental degradation but are often the most affected, must have a voice in shaping global policies. The principle of climate justice, which calls for fair distribution of the burdens and benefits of climate action, must guide our approach to global governance in the Anthropocene. While global institutions play a critical role in managing the Anthropocene, individuals also have the power to make a difference. Personal choices about energy use, transportation, diet, and consumption can collectively reduce humanity's environmental impact. The rise of grassroots movements such as Fridays for Future and Extinction Rebellion shows that individuals can mobilize for change and influence political agendas. Education and awareness are key to empowering individuals to take action. Understanding the science behind climate change, biodiversity loss, and resource depletion can inspire people to make more sustainable choices in their daily lives. But beyond individual actions, collective efforts, such as supporting environmental policies, voting for leaders who prioritize sustainability, and participating in community initiatives, are essential for driving systemic change. The Anthropocene represents a critical juncture in Earth's history, a time when humanity's impact on the planet is undeniable, but also when the potential for positive change is immense. As we confront the environmental challenges of our time, we are also witnessing a growing awareness of the need for stewardship, cooperation, and innovation. This planetary awakening is fueled by a new generation of thinkers, scientists, activists, and leaders who are reimagining humanity's role on Earth. It is a time of unprecedented possibility, where the choices we make will determine the future of life on this planet. The Anthropocene is not just a story of destruction, it is also a story of resilience, adaptation, and hope. By embracing our responsibility as stewards of the Earth, we can create a future where both people and the planet thrive. A future where progress is measured not by material wealth, but by the health and well-being of all living systems. Over the course of billions of years, Earth's surface has been shaped by the movement of tectonic plates. These massive slabs of the Earth's crust float on the semi-fluid layer of the mantle, slowly shifting and colliding, pulling apart and reshaping the face of the planet. This process, known as plate tectonics, has created the continents, mountain ranges, and ocean basins that define Earth today. The supercontinents, such as Pangaea, Gondwana, and Laurasia, provide fascinating insights into how Earth's geography has evolved over deep time. Pangaea, the most recent supercontinent, formed about 335 million years ago and began to break apart around 175 million years ago. This breakup reshaped ocean currents, altered climate patterns, and influenced the distribution of species, which were forced to adapt to the changing environment. Plate tectonics is also responsible for some of Earth's most dramatic phenomena, including earthquakes, volcanoes, and the formation of mountains. The collision of the Indian and Eurasian plates, for example, gave rise to the Himalayas, the tallest mountain range in the world. This ongoing tectonic activity continues to shape Earth's surface, reminding us that the planet is a dynamic, ever-evolving system. Volcanic activity is one of the most powerful forces shaping Earth's surface. Volcanoes form when molten rock or magma rises from beneath the Earth's crust and erupts onto the surface. These eruptions can be both destructive and creative, as they can wipe out ecosystems and bury landscapes in ash and lava, but also create new land and fertile soils. Throughout Earth's history, volcanic eruptions have played a critical role in shaping the climate and atmosphere. Massive volcanic events known as flood basalts have released enormous amounts of greenhouse gases into the atmosphere, leading to periods of global warming. At other times, volcanic eruptions have injected sulfur aerosols into the atmosphere, reflecting sunlight and causing temporary cooling. One of the most famous examples of volcanic activity altering the climate is the eruption of Mount Tambora in 1815, which caused the year without a summer in 1816. The volcanic ash and gases ejected into the atmosphere led to crop failures, food shortages, and extreme weather conditions around the world. This event is a stark reminder of how Earth's internal processes can have far-reaching consequences for the biosphere and human societies. Ice ages are periods in Earth's history when global temperatures drop significantly, leading to the expansion of polar ice sheets and glaciers. These frozen epochs have occurred multiple times throughout Earth's history, most recently during the Quaternary period, which began about 2.6 million years ago and continues to the present. During ice ages, large portions of Earth's landmass are covered by ice, which alters the planet's albedo and further cools the climate. These periods of glaciation are punctuated by warmer interglacial periods, during which ice sheets retreat and global temperatures rise. The cycles of glaciation are driven by a combination of factors, including changes in Earth's orbit, axial tilt, and the composition of the atmosphere. The most recent ice age ended about 12,000 years ago, ushering in the current Holocene epoch. The retreat of the glaciers transformed the landscape, carving out valleys, shaping coastlines, and creating fertile plains. It also created conditions that allowed human civilizations to flourish, as stable climates and abundant resources supported the development of agriculture and permanent settlements. Throughout Earth's history, life has faced several catastrophic mass extinctions which have wiped out vast numbers of species and reshaped the course of evolution. These mass extinctions were triggered by a range of factors, including asteroid impacts, volcanic eruptions, and dramatic climate shifts. Yet despite the devastation, life has always found a way to recover and adapt. The Permian-Triassic extinction, which occurred around 252 million years ago, is known as the Great Dying and was the most severe extinction event in Earth's history. It is estimated that 90% of all marine species and 70% of terrestrial species were wiped out. The exact cause of this extinction is still debated, but many scientists believe it was linked to massive volcanic activity in Siberia, which released vast amounts of greenhouse gases and triggered global warming. Following this extinction, life rebounded in spectacular fashion. The survivors of the Permian-Triassic extinction laid the groundwork for the rise of the dinosaurs, which would dominate Earth for the next 160 million years. The Cretaceous-Paleogene extinction, which wiped out the dinosaurs 66 million years ago, cleared the way for mammals to rise to prominence, eventually leading to the emergence of humans. These extinction events highlight the resilience of life on Earth. While mass extinctions cause dramatic losses of biodiversity, they also open up new ecological niches and opportunities for evolution. The story of life on Earth is one of adaptation and renewal, shaped by both catastrophic events and gradual environmental changes. Earth's atmosphere has undergone dramatic changes since the planet's formation. In its early history, Earth's atmosphere was dominated by gases such as hydrogen, helium, methane, and ammonia. However, this primordial atmosphere was gradually lost to space, and volcanic outgassing gave rise to a new atmosphere composed of water vapor, carbon dioxide, nitrogen, and trace gases. A major turning point in Earth's atmospheric history occurred around 2.4 billion years ago with the Great Oxidation Event. During this time, cyanobacteria began to produce oxygen through photosynthesis, releasing it into the atmosphere. This dramatic increase in oxygen levels transformed the planet, leading to the formation of the ozone layer, which protected life from harmful ultraviolet radiation and allowed more complex organisms to evolve. The oxygenation of Earth's atmosphere was a double-edged sword. While it enabled the evolution of aerobic life, it also caused a mass extinction of anaerobic organisms that could not survive in an oxygen-rich environment. This event, known as the oxygen catastrophe, is a reminder of how changes in atmospheric composition can have profound effects on life. Earth's climate is regulated by a complex interplay of factors, including solar radiation, atmospheric composition, and the reflectivity of Earth's surface. The balance between incoming solar energy and outgoing heat is critical for maintaining Earth's average temperature. When this balance is disrupted by volcanic eruptions, changes in Earth's orbit, or human activities, Earth's climate can shift dramatically. One of the most important natural drivers of climate oscillations is the Milankovitch cycles, which describe variations in Earth's orbit and axial tilt. These cycles occur over tens of thousands to hundreds of thousands of years and have been linked to the timing of ice ages and interglacial periods. By altering the amount of solar energy reaching Earth's surface, these cycles can trigger periods of warming or cooling. However, human activities are now disrupting this natural thermal balance. The burning of fossil fuels has led to a sharp increase in atmospheric carbon dioxide and other greenhouse gases, which trap heat in the atmosphere and cause global temperatures to rise. This human-induced climate change is occurring at an unprecedented rate, overwhelming Earth's natural feedback mechanisms and leading to widespread environmental impacts. The oceans play a central role in regulating Earth's climate. They absorb and store vast amounts of solar energy, distribute heat around the planet through currents, and act as a buffer against climate change by absorbing carbon dioxide from the atmosphere. The ocean atmosphere system is tightly interconnected, with changes in one often leading to changes in the other. The circulation of ocean currents, such as the Gulf Stream, helps regulate global climate by transporting warm water from the tropics to higher latitudes. This redistribution of heat helps moderate temperatures in regions like Europe and North America. However, as global temperatures rise, ocean circulation patterns are being disrupted, with potentially far-reaching consequences for weather systems and ecosystems. In addition to regulating climate, the oceans are also key to the carbon cycle. Phytoplankton, microscopic organisms in the ocean, play a crucial role in absorbing carbon dioxide through photosynthesis. When these organisms die, some of the carbon sinks to the ocean floor, where it is stored for long periods of time. However, as ocean temperatures rise and acidification increases, the health of marine ecosystems is being threatened, reducing the ocean's ability to act as a carbon sink. The carbon cycle is one of the most important biogeochemical cycles on Earth, regulating the movement of carbon between the atmosphere, oceans, soil, and living organisms. Carbon is the building block of life, and its movement through Earth's systems is critical for maintaining the balance of the planet's climate and ecosystems. Plants, through the process of photosynthesis, absorb carbon dioxide from the atmosphere and convert it into organic matter. This carbon is then passed through the food chain as animals eat plants and other animals. When plants and animals die, their carbon-rich bodies decompose, returning carbon to the soil or releasing it back into the atmosphere as carbon dioxide. Some of this carbon is buried and stored for millions of years in the form of fossil fuels. Human activities, particularly the burning of fossil fuels, have disrupted the carbon cycle by releasing large amounts of stored carbon into the atmosphere in a relatively short period of time. This excess carbon dioxide is the primary driver of climate change, as it enhances the greenhouse effect and raises global temperatures. The water cycle is the continuous movement of water between Earth's atmosphere, surface, and underground reservoirs. This cycle is essential for distributing heat, regulating climate, and supporting life. Water evaporates from oceans, lakes, and rivers, rises into the atmosphere, condenses into clouds, and falls back to Earth as precipitation. It then flows through rivers and streams, seeps into the ground, or returns to the ocean, completing the cycle. Water is not evenly distributed across the planet, and changes in the water cycle due to climate change are leading to more extreme weather events. Droughts are becoming more frequent in some regions, while other areas are experiencing more intense storms and flooding. These changes have significant implications for agriculture, freshwater availability, and the overall stability of ecosystems. The water cycle is also closely linked to the carbon cycle. Oceans absorb large amounts of carbon dioxide from the atmosphere, helping to moderate climate change. However, as ocean temperatures rise and acidification increases, the ability of the oceans to absorb carbon is decreasing, creating a feedback loop that accelerates global warming. Earth's systems are interconnected in complex and dynamic ways. The atmosphere, oceans, land, and living organisms all interact to create the conditions necessary for life. Changes in one system can have cascading effects on others, creating feedback loops that amplify or dampen environmental changes. For example, deforestation not only reduces biodiversity but also affects the carbon and water cycles. Trees absorb carbon dioxide and release water vapor, which helps regulate the climate. When forests are cut down, This natural regulation is disrupted, leading to higher carbon dioxide levels and changes in local and global weather patterns. Understanding the interconnectedness of Earth's systems is essential for addressing the environmental challenges we face. Efforts to mitigate climate change, protect biodiversity, and manage natural resources must take into account the complex interactions between these systems and the potential for unintended consequences. Beneath Earth's surface lies a dynamic system that generates one of the planet's most vital protective mechanisms, the magnetic field. Earth's magnetic field is created by the movement of molten iron and nickel in the outer core, a process known as the geodynamo. As these molten metals circulate, they generate electrical currents, which in turn produce a magnetic field that extends far beyond the planet's surface, enveloping Earth like a shield. This magnetic field is crucial for life on Earth. It protects the planet from harmful solar radiation and cosmic rays, which would otherwise strip away the atmosphere and bombard the surface with intense radiation. Without the magnetic field, Earth could be a barren, lifeless world, similar to Mars, which lost its magnetic field billions of years ago and, with it, much of its atmosphere. Earth's magnetic field extends far into space, forming the magnetosphere, a vast, teardrop-shaped region that deflects charged particles from the Sun. As the solar wind, a stream of charged particles emitted by the Sun, approaches Earth, it is deflected by the magnetosphere, protecting the planet from these potentially harmful particles. When the solar wind interacts with Earth's magnetic field, it creates stunning natural phenomena known as auroras, or the northern and southern lights. These displays of light occur when charged particles from the Sun are funneled towards the poles by Earth's magnetic field, where they collide with gases in the upper atmosphere, causing them to glow. However, the magnetosphere is not impervious to disruption. Solar storms, also known as geomagnetic storms, can temporarily overwhelm the magnetosphere, causing fluctuations in Earth's magnetic field. These storms can disrupt satellite communications, power grids, and even pose risks to astronauts in space. As our reliance on technology grows, understanding and predicting the behavior of the magnetosphere has become increasingly important. One of the most intriguing features of Earth's magnetic field is its tendency to reverse polarity over geological time. During a magnetic reversal, the positions of the magnetic north and south poles swap, meaning that a compass pointing north today would point south during a reversal. These reversals, known as geomagnetic reversals, have occurred many times in Earth's history, with the most recent one occurring about 780,000 years ago. The exact cause of these reversals is still not fully understood, but they are believed to be linked to changes in the flow of molten iron within Earth's outer core. During a reversal, the strength of the magnetic field weakens, sometimes to the point where it nearly disappears. This temporary weakening of the magnetic field raises questions about how Earth's atmosphere and life might be affected. Although geomagnetic reversals are a natural part of Earth's geological processes, there is no evidence to suggest that they have led to mass extinctions or significant disruptions to life. However, during a reversal, Earth's magnetic field may be more vulnerable to solar radiation, which could have implications for modern technology and infrastructure. Understanding the timing and effects of magnetic reversals remains an area of active research. For centuries, Earth's magnetic field has played a crucial role in human navigation. The invention of the compass, which relies on the alignment of a magnetized needle with Earth's magnetic field, revolutionized sea travel and exploration. Long before the advent of GPS and satellite navigation, the magnetic field guided sailors across oceans and explorers across uncharted lands. Today, a magnetic field remains essential for modern technology. Satellites, spacecraft, and communication systems rely on accurate measurements of the magnetic field for orientation and navigation. Scientists also study the magnetic field to understand processes happening deep within Earth's core, providing insights into the inner workings of our planet. As we continue to explore space, understanding Earth's magnetic field will become even more critical. Future missions to the Moon, Mars, and beyond will need to account for the protection that Earth's magnetic field provides, as astronauts traveling beyond its reach will be exposed to higher levels of cosmic and solar radiation. Developing technologies to shield spacecraft and habitats from radiation will be essential for the future of space exploration. Earth's oceans are ancient, having formed billions of years ago as the planet cooled and water vapor condensed to fill vast basins in the Earth's crust. The origins of this water remain a topic of scientific investigation, with some theories suggesting that water was delivered by comets and asteroids during the early formation of the planet, while others propose that water emerged from volcanic outgassing from the planet's interior. Regardless of their origins, Earth's oceans have shaped the course of planetary history and evolution. Covering more than 70% of Earth's surface, the oceans are the largest reservoirs of water on the planet and play a central role in regulating climate, supporting biodiversity, and driving the global water cycle. They are, in many ways, the blue heart of the planet, essential for life as we know it. The oceans play a critical role in regulating Earth's climate by absorbing, storing, and redistributing heat from the sun. Ocean currents act as giant conveyor belts, transporting warm water from the equator towards the poles and cold water from the poles back to the equator. This heat exchange helps to moderate global temperatures, making Earth more habitable. The oceans also absorb vast amounts of carbon dioxide from the atmosphere, helping to mitigate the effects of climate change. Phytoplankton, tiny marine organisms, use carbon dioxide for photosynthesis, removing it from the atmosphere and incorporating it into the marine food web. Some of this carbon eventually sinks to the ocean floor, where it can be stored for long periods of time, creating a natural carbon sink. However, as global temperatures rise and carbon dioxide levels increase, the oceans are becoming warmer and more acidic. These changes threaten marine ecosystems, particularly coral reefs, which are highly sensitive to temperature and acidity. Coral bleaching caused by rising ocean temperatures is already having devastating effects on biodiversity. As the oceans continue to absorb more carbon dioxide, acidification could disrupt the delicate balance of marine ecosystems, with far-reaching consequences for global food security and the health of the planet. The oceans are central to the global water cycle, which distributes water across the planet through evaporation, condensation, and precipitation. Solar energy causes water to evaporate from the surface of the oceans, forming clouds that release rain and snow over land. This precipitation replenishes freshwater sources, such as rivers, lakes, and aquifers, which are essential for drinking water, agriculture, and industry. The oceans also influence weather patterns and storm systems. Hurricanes, typhoons, and tropical storms are fueled by warm ocean waters, which provide the energy needed to drive these powerful storms. Changes in ocean temperature and circulation patterns, such as El Niño and La Niña, can have wide-ranging impacts on global weather, affecting rainfall, droughts, and even agricultural yields. As climate change accelerates, these weather systems are becoming more intense and unpredictable. Rising sea levels, caused by the melting of polar ice and the expansion of seawater as it warms, are increasing the risk of flooding in coastal regions. Storm surges driven by stronger hurricanes and typhoons are also threatening coastal communities and ecosystems. Understanding and mitigating the impacts of these changes will be a critical challenge for the future. Life on Earth began in the oceans, and the rich biodiversity of marine ecosystems continues to support a vast array of life forms. The ocean's immense variety of habitats, from the sunlit surface waters to the dark depths of the abyssal plains, provides homes for species that are uniquely adapted to their environments. Coral reefs, kelp forests, deep-sea hydrothermal vents, and open ocean ecosystems each harbor distinct communities of life, many of which are still largely unexplored. The discovery of deep-sea hydrothermal vents in the 1970s revolutionized our understanding of where and how life could thrive. These vents, located at the boundaries of tectonic plates, release superheated water rich in minerals, creating an environment where life exists not through photosynthesis but through chemosynthesis, a process in which bacteria derive energy from chemical reactions. These vent communities have revealed the incredible adaptability of life and suggest that similar environments may exist on other ocean-bearing worlds, such as Jupiter's moon, Europa, or Saturn's moon, Enceladus. The oceans are under threat from human activities. Overfishing, plastic pollution, habitat destruction, and the impacts of climate change are placing immense pressure on marine ecosystems. The health of the oceans is not only critical for marine species, but also for human societies, which rely on the oceans for food, transportation, and livelihoods. Protecting the oceans and ensuring their resilience in the face of environmental challenges is essential for sustaining life on Earth. As the global population grows and demand for resources increases, the concept of the blue economy has emerged as a framework for using ocean resources sustainably. The blue economy encompasses a wide range of activities, including fisheries, aquaculture, shipping, tourism, and offshore renewable energy. The goal is to balance economic growth with the conservation of marine ecosystems, ensuring that the oceans continue to provide resources for future generations. Sustainable fisheries and aquaculture practices are critical to maintaining food security while protecting marine biodiversity. Overfishing has depleted many fish populations, threatening the balance of marine ecosystems and the livelihoods of millions of people who depend on fishing for income. By adopting sustainable fishing practices, such as setting catch limits and protecting critical habitats, we can help restore fish populations and ensure the long-term health of marine ecosystems. Offshore renewable energy, particularly wind and tidal power, offers promising opportunities for reducing our reliance on fossil fuels while minimizing environmental impact. These technologies harness the power of the ocean to generate electricity, providing a clean and renewable source of energy that can help mitigate climate change. Marine biodiversity is essential for the health of ocean ecosystems and the services they provide. Coral reefs, for example, support 1/4 of all marine species despite covering less than 1% of the ocean floor. Yet coral reefs are among the most threatened ecosystems on the planet, facing pressures from climate change, pollution, overfishing, and coastal development. International efforts to protect marine biodiversity have gained momentum in recent years. Marine Protected Areas (MPAs) have been established to safeguard critical habitats, allowing ecosystems to recover and species to thrive. However, only a small fraction of the world's oceans is currently protected, and expanding these areas will be crucial for preserving biodiversity in the face of growing environmental challenges. Global cooperation is also essential for addressing issues such as plastic pollution, which affects every corner of the ocean. The Great Pacific Garbage Patch, a massive accumulation of plastic debris, is just one example of the scale of the problem. Reducing plastic waste, improving recycling systems, and developing alternatives to single-use plastics are important steps in tackling the ocean plastic crisis. Advances in science and technology are transforming our understanding of the oceans and providing new tools for conservation. Autonomous underwater vehicles (AUVs), remotely operated vehicles (ROVs), and satellite technology are enabling scientists to explore and monitor the oceans in ways that were previously unimaginable. These technologies allow us to map the ocean floor, track the movements of marine species, and monitor changes in ocean temperature, salinity, and currents. Marine research is also uncovering new species and ecosystems, expanding our knowledge of the deep sea, which remains one of the least explored regions on Earth. The study of marine genetics and biodiversity has the potential to revolutionize fields such as medicine, biotechnology, and environmental science. At the same time, citizen science initiatives are empowering individuals to contribute to ocean conservation efforts. Programs such as beach cleanups, biodiversity surveys, and plastic waste tracking allow people to engage directly with the health of the oceans and raise awareness about the importance of protecting marine ecosystems. The future of Earth's oceans will be shaped by the decisions we make today. Ensuring the sustainability of the oceans requires a holistic approach that addresses the interconnected challenges of climate change, pollution, overfishing, and habitat destruction. By embracing sustainable practices, protecting marine biodiversity, and advancing scientific research, we can safeguard the health of the oceans for future generations. The oceans have sustained life on Earth for billions of years, providing food, climate regulation, and a wealth of resources. They are a vital part of Earth's natural systems, and their continued health is essential for the well-being of all life on the planet. As we move forward, the challenge is to find ways to use the ocean's resources responsibly, while preserving the ecosystems that make life on Earth possible. The oceans are not just the planet's largest ecosystems, they are the life support system for the entire Earth. Protecting them is not an option. It is a necessity for the survival of our planet and the future of humanity. While we live on Earth's surface, the planet's interior remains largely a mystery. Shrouded in layers of rock and molten metal that stretch down nearly 6,400 kilometers to its core, Earth is made up of several distinct layers: the crust, mantle, outer core, and inner core, each playing a crucial role in shaping the planet's behavior and characteristics. The crust, the outermost layer, is the thinnest, ranging from 5 kilometers under the oceans to 70 kilometers under the continents. It is where life exists and where human civilization has developed. Beneath the crust lies the mantle, a vast, solid layer of silicate rock that behaves plastically over long timescales. The mantle makes up about 84% of Earth's volume and is constantly in slow motion, driving the movement of tectonic plates through the process of convection. Deeper still lies the outer core, a molten sea of iron and nickel. It is this liquid metal that generates Earth's magnetic field through the dynamo effect, a process driven by the convection currents within the outer core. Finally, at the center of the planet, we find the solid inner core, a dense ball of iron and nickel under immense pressure. Temperatures in the inner core reach up to 5,700 degrees Celsius, hotter than the surface of the Sun. Though we cannot directly observe the inner Earth, geologists study seismic waves generated by earthquakes to map its structure. These waves behave differently as they pass through different materials, allowing scientists to infer the composition and properties of Earth's interior. This ongoing research is helping to reveal the secrets of the deep Earth and its influence on the planet's surface. The theory of plate tectonics, developed in the mid-20th century, revolutionized our understanding of how Earth's surface changes over time. Earth's lithosphere, the rigid outer layer that includes the crust and the uppermost mantle, is divided into tectonic plates that float on the semi-fluid asthenosphere beneath them. These plates are in constant motion, albeit at rates of just a few centimeters per year, driven by heat from the mantle. There are three main types of plate boundaries: divergent, where plates move apart as seen at mid-ocean ridges; convergent, where plates collide forming mountain ranges or deep ocean trenches; and transform, where plates slide past each other horizontally, as in the case of the San Andreas Fault in California. These interactions create much of Earth's geological activity, including earthquakes, volcanic eruptions, and the formation of mountains. The movement of tectonic plates has shaped the planet's surface for billions of years, giving rise to continents and oceans. The process is responsible for the creation of the world's tallest peaks, like the Himalayas, and the deepest ocean trenches, like the Mariana Trench. The recycling of oceanic crust back into the mantle at subduction zones, and the constant generation of new crust at divergent boundaries maintain the planet's dynamic equilibrium. Plate tectonics also plays a crucial role in Earth's carbon cycle, regulating the amount of carbon dioxide in the atmosphere. As tectonic plates move, volcanic activity releases carbon dioxide, while the weathering of rocks absorbs it. This long-term cycle has helped stabilize Earth's climate over geological timescales, enabling the planet to support life. Earthquakes and volcanic eruptions are among the most dramatic manifestations of Earth's internal forces. These events are driven by the movement of tectonic plates and the heat and pressure that build up deep within the Earth. Earthquakes occur when stress builds up along faults or fractures in the Earth's crust and is suddenly released. The energy radiates outward as seismic waves, shaking the ground and sometimes causing widespread destruction. The magnitude of an earthquake is measured on the Richter scale, with each increase in magnitude representing a tenfold increase in the energy released. Some of the most powerful earthquakes occur at convergent boundaries, where one tectonic plate is forced beneath another in a process known as subduction. These regions, known as subduction zones, are also prone to volcanic activity, as the descending plate melts and forms magma that rises to the surface. This process has created some of the world's most active volcanic regions, such as the Pacific Ring of Fire. Volcanoes are windows into Earth's interior, where molten rock, ash, and gases escape from the mantle to the surface. While volcanic eruptions can be catastrophic, they also play a vital role in shaping the planet. Volcanic eruptions have formed entire islands, such as those in Hawaii, and their ash deposits can fertilize soils, supporting agriculture and ecosystems. Over geological time, volcanic activity has even contributed to the formation of Earth's atmosphere and oceans. The mantle, though solid, is in constant motion, slowly convecting over millions of years. Heat from the core drives this convection, causing hot material to rise toward the surface while cooler material sinks. This process powers plate tectonics and is responsible for the movement of continents, the formation of mountain ranges, and the creation of new ocean floor. The mantle also plays a key role in the cycling of elements between Earth's interior and its surface. Elements like carbon, nitrogen, and sulfur, which are critical for life, are cycled between the mantle, the crust, and the atmosphere through processes like volcanic eruptions and the subduction of oceanic plates. This deep Earth cycling of elements has profound implications for Earth's habitability, influencing everything from climate to the availability of resources. Mantle plumes, upwellings of hot material from deep within the mantle, are responsible for creating volcanic hotspots, such as those that form the Hawaiian Islands. These plumes are thought to originate near the boundary between the mantle and the outer core, and they provide a direct connection between Earth's deep interior and its surface. The mantle's slow, inexorable movements shape the planet's surface and have a profound impact on the evolution of Earth's climate, continents, and life. Understanding these processes is key to understanding the long-term evolution of our planet. Earth's atmosphere has evolved dramatically over its 4.5 billion year history. In its earliest stages, the atmosphere was likely composed of hydrogen and helium, but this primordial atmosphere was lost to space due to the planet's relatively weak gravity and the intense solar wind of the young sun. The atmosphere we know today began to take shape through volcanic outgassing, as early volcanic activity released gases like water vapor, carbon dioxide, and nitrogen. Over time, these gases cooled and condensed, forming the oceans and creating a new atmosphere. This early atmosphere was still inhospitable to life as we know it, lacking the oxygen that would later become crucial for the development of complex organisms. A major transformation occurred with the rise of photosynthetic organisms such as cyanobacteria around 2.4 billion years ago. These organisms began to produce oxygen as a byproduct of photosynthesis, gradually enriching the atmosphere with oxygen in an event known as the Great Oxidation. This shift paved the way for the evolution of aerobic organisms and the development of the protective ozone layer, which shields life from harmful ultraviolet radiation. Earth's atmosphere acts as a thermal blanket, trapping heat from the sun and maintaining temperatures that allow liquid water to exist. Known as the greenhouse effect, is essential for sustaining life. Without it, Earth's surface would be too cold for most life forms to survive. The greenhouse effect is driven by gases in the atmosphere, such as carbon dioxide CO2, methane CH4, and water vapor H2O, which absorb and re-radiate heat. While these gases make up only a small fraction of the atmosphere, they have a significant impact on Earth's temperature. Water vapor is the most abundant greenhouse gas, but carbon dioxide is particularly important because it persists in the atmosphere for long periods and has a powerful warming effect. For much of Earth's history, natural processes have regulated the levels of greenhouse gases, maintaining a balance that has allowed life to thrive. However, human activities, especially the burning of fossil fuels and deforestation, are increasing the concentration of greenhouse gases in the atmosphere, intensifying the greenhouse effect and leading to global warming. The atmosphere is a key player in Earth's climate system. It interacts with the oceans, land, and ice to distribute heat and moisture around the planet, shaping weather patterns and climate zones. Changes in the composition of the atmosphere, whether from natural processes or human activities, can have far-reaching impacts on global climate. The rapid increase in greenhouse gas concentrations is causing Earth's climate to warm at an unprecedented rate. This warming is leading to more frequent and intense heat waves, changing precipitation patterns, melting glaciers and polar ice, and raising sea levels. These changes are disrupting ecosystems, threatening food and water security and increasing the frequency of extreme weather events. The climate system is complex, and feedback mechanisms can amplify or mitigate the effects of warming. For example, as ice melts, it exposes darker surfaces, such as ocean water or land, which absorb more heat, further accelerating warming. At the same time, warming temperatures can increase cloud cover, which reflects sunlight and provides a cooling effect. Understanding these feedbacks is critical for predicting the future trajectory of climate change and its impacts on life and human societies. The protection of Earth's atmosphere is one of the greatest challenges of the 21st century. Addressing climate change requires reducing greenhouse gas emissions, transitioning to renewable energy sources, and protecting natural ecosystems that act as carbon sinks, such as forests and wetlands. International agreements, such as the Paris Climate Agreement, represent a global effort to limit warming to below 2 degrees Celsius above pre-industrial levels, with the aim of avoiding the most catastrophic effects of climate change. Achieving these goals will require concerted action from governments, industries, and individuals around the world. Technological innovations such as carbon capture and storage (CCS) offer potential solutions for reducing atmospheric carbon dioxide levels, while advances in renewable energy such as solar, wind, and geothermal power are helping to shift economies away from fossil fuels. However, the transition to a sustainable future will require not only technological solutions, but also changes in consumption patterns, land use, and energy policies. Preserving Earth's atmosphere is not just an environmental issue, it is a matter of social and economic justice. The impacts of climate change disproportionately affect vulnerable populations, particularly in developing countries that have contributed the least to global emissions. Addressing climate change requires a fair and equitable approach that ensures all nations have the resources and support they need to adapt to a changing world. Earth is a planet unlike any other we know, a marvel of complexity, beauty, and resilience. Over billions of years, it has evolved through cycles of creation and destruction, shaped by cosmic forces, geological upheavals, and the emergence of life itself. From the depths of its oceans to the outer reaches of its atmosphere, Earth's intricate systems have supported the delicate balance necessary for life to thrive. Today, humanity is a defining force on this planet. Our technological advances and industrial growth have transformed landscapes, altered ecosystems, and significantly impacted Earth's climate. As we enter the Anthropocene, a new chapter in Earth's history, we face a pivotal moment. Our actions will determine the future of the planet and the legacy we leave behind for generations to come. Earth's journey is one of constant evolution. It has endured mass extinctions, ice ages, and dramatic shifts in climate, yet life has always found a way to adapt and flourish. But the unprecedented scale and speed of human impact now place Earth at a crossroads. Our understanding of the planet's systems, its atmosphere, oceans, land, and living organisms gives us both the power and the responsibility to protect and restore it. The challenges we face are immense. Climate change, biodiversity loss, pollution, and resource depletion threaten the very foundations of life on Earth. Yet within these challenges lies an opportunity for profound transformation. By embracing sustainability, renewable energy, conservation, and responsible stewardship, we can create a future where both people and the planet thrive. Preserving Earth is not merely an environmental obligation, it is a moral imperative. It is about ensuring the survival of life in all its forms, about protecting the ecosystems that sustain us, and about passing on a vibrant, healthy planet to future generations. Earth's resources are finite, and its systems fragile, but with collective action and a global commitment to change, we can ensure that this extraordinary world continues to be a sanctuary for life. As we look ahead, the path we choose will define our legacy. Will we be remembered as the generation that protected the Earth and ensured its future, or as the generation that allowed it to falter? The answers lie in our hands. In the vast expanse of the universe, Earth remains our only home, a rare and precious world teeming with life. Let us recognize its value, honor its resilience, and rise to the challenge of safeguarding its future. Our journey on this planet is intertwined with its fate. By acting with foresight, care, and responsibility, we can ensure that Earth's story continues, a beacon of life in the cosmos for millennia to come. The future of Earth is our shared responsibility. Let us protect this planet with the reverence it deserves and secure its place as a thriving, life-sustaining world, now and forever.